All right, let's move on to our next example. Here we're going to need the quotient rule because notice that there is a minus sign between them and both of the bases of the logs are 4. So since they're the same number, we can combine them using the quotient rule. So the quotient rule tells us that we can combine that into log base 4 of 4x minus 8 over negative 9x minus 4, and that is equal to 3. Now, from here, we're trying to solve for x, so we want to get rid of the log, and we're going to use that by using Bay. So if we use Bay, then we get 4 to the third power is equal to 4x minus 8 over negative 9x minus 4. And we're going to want to simplify that now. So 4 to the third power is 64. What I'm going to do from here is I'm going to multiply both sides by the denominator. I missed a plus sign, sorry, that should be plus all around. And then I'm going to multiply this side by negative 9x plus 4. And if we do that, then our equation will then look like 64 times negative 9x plus 4 is equal to 4x minus 8. Okay, so if I distribute that 64, then we get negative 576x plus 256 is equal to 4x minus 8. And then I can combine like terms on both sides of the equation, and we'll get negative 580x is equal to negative 264. And if I divide negative 580 on both sides, we'll get 264 over 580. If you reduce that, that's 66 over 145. And if you throw that into your calculator, it's approximately 0.46. Now, will that work in our equation? I'm going to take that and plug it in here, and that is, if we plug that in for x there, that's going to make that slightly to the left of negative 4, and so the overall thing is going to be negative 4. So that solution actually does not work, and so to answer this question, we would say that there are no real solutions. Because the x that we solve for, we plug that back into the original equation, and we found that it would give us a log of some negative number, which we've discussed earlier. You cannot take the log of a negative number, so we say that there are no real solutions. Okay, let's move on to part C. From here, we can use the rule that says that if we take the log of one side, we can take the log of the other side. And so I'm going to take the natural log of both sides. Now here, we can actually utilize the power rule. And it says that, if we have an exponent, we can bring it on the outside and multiply. So the left-hand side is actually equivalent to 8x times the natural log of e, and that is equal to the natural log of 14.2. Now, I'm going to leave it up to you. I'd like you to think about why the natural log of e is equal to 1. So take a moment if you are not sure why, and maybe write it in exponential form, but don't just take my word for it. The natural log of e is equal to 1, so we're going to be left with 8x times 1, which is just 8x, is equal to the natural log of 14.2. And then from here, I'm going to divide both sides by 8. So we get x is equal to the natural log of 14.2 over 8. Now, sometimes the homework on WAMAP will want you to enter it as an exact value. And so if that's the case, then you would just plug in the natural log of 14.2 over 8. And then sometimes it requests that you plug in an approximation. And so that's where you would throw that into your calculator and give it a rounded number. So I threw that into my calculator and I got that that was approximately 0.3317. So depending on how many decimals it might ask for, either of these might suffice. Okay. All right, part D says 9 over 4 times log base 4 of x is equal to 8. So the first thing I'm going to do to try to get x by itself is I'm going to multiply both sides of the equation by the reciprocal of that fraction there. So I'm going to multiply by 4/9. And if we do that, we get log base 4 of x is equal to 32 over 9. And then if we rewrite this in exponential form, we get that x is equal to 4 to the power of 32 over 9. And you could either leave your answer like that, or depending if it wants a decimal approximation, that is equivalent to so I threw that into my calculator and I got 138.2476. Okay. Okay, example 7 talks about the Richter scale, and this should be a point of interest for us because we live in the state of Washington and we experience earthquakes from time to time. And scientists are predicting that we're actually going to experience a rather large earthquake in the near future. So this might be something that you might be interested in. The Richter scale is used to measure the intensity of an earthquake. The magnitude on the Richter scale of an earthquake of intensity I is given by that equation where I sub 0 is a certain minimum intensity used for comparison. So part A says find R if I is 15,800,000 times as great as I sub 0. So we would get R equals log of 15,800,000 times as great as I sub 0 divided by I sub 0. And what's really nice there is these will divide out. So really we're just evaluating the log of 15,800,000. And if you throw that into your calculator, let's see what we get. So I got that it was approximately 7.1987. So hopefully you've heard on the news before, in Japan they experienced a magnitude 8.1 earthquake, or something like that. And so an earthquake of magnitude 7.19 is a pretty destructive earthquake. So that's not to be taken lightly. Okay, so that was part A. Let's look at part B. It says, as of 2017, the 1964 Alaskan earthquake was the most violent U.S. earthquake and one of the strongest ever. It measured 9.2 on the Richter scale. Find the intensity of the 1964 Alaskan earthquake. So if we use our formula, we're going to replace the R value with 9.2, and we're trying to solve for I, even though we don't know what I sub 0 is either. So let's see if we can work that out. So we have 9.2 equals log of I over I sub 0. So I'm going to rewrite this so that we can use Bay. We got to switch the order. So B, A, E. Now remember, if there's no base given and it just says log, that is a scenario where we assume the base to be 10 and that we're dealing with the common logarithm. So we would say 10 to the power of 9.2 is equal to I divided by I sub 0. And then if we solved for I, we would get I equals 10 to the power of 9.2 times I sub 0. And if you throw that number into your calculator, that simplifies to 1,580,000,000 times I sub 0. So from here, since we don't know what I sub 0 is, we can say that the intensity of the 1964 Alaskan earthquake was 1,580,000,000 times as intense as I sub 0.